Okay, good afternoon, everybody. So for today's lecture, what we are going to do is we are going to briefly go over the last problem from last lecture regarding red-black trees. Then we are going to introduce the idea of Amoritized analysis and probability into tree construction. We're going to go over two new types of data structures. The first one is called a Splay tree. And the term splay means that once we insert an element into the splay tree, or if we access an element in the splay tree, that element is going to be splayed or moved up to the top of the tree. And we're going to use this to start going over a concept, a couple of concepts called temporal and spatial locality. So for those of you who are taking computer architecture, you're no doubt aware of that by now. For those of you taking logic design and you're starting to get into memory and the albacore architecture, you're going to start hearing about that. Then we're going to talk about probabilistic trees and how that can be used to improve balance using probabilities when we insert elements. So it's going to be combining the elements of insertion and sorting in a binary search tree, but we're also going to revisit the ideas that we got from heaps. So a common question I received when we were going over max and min heaps is, are there benefits to making those pointers instead of just using an underlying dynamic array? And the benefit of doing that, we're going to investigate, is we can use probabilities to be able to provide those insertions. And we're going to call that a tree. The first thing I want to do is I want to go back over the last problem in the lecture. So it's a red-black tree problem. And I'm going to go over this in the animation. So the insertions, I'm going to go over the insertions quickly, but then I'm going to go over the deletions in more detail. So first we insert 5. 16 will become the right child of 5 and will become a red node. Then we insert 12. And 12 is going to become red, and it's going to be the right child of 16. I'm sorry, the left child of 16, and then it will be rotated, and then we get that case where the parent and grandparent are recolored. Then we have 14. 14 would become the left child of 16, will also be red. We have the scenario where the parent and uncle are both red. We recolor the parent and uncle to black, and we recolor the grandparent to red. And then the final thing, the root 12 was recolored. So we have 14 in there. Now I'm going to insert 13. 13 will become a red left child of 14. We have this zig-zag scenario, so we move it up, and 14 becomes black, and its left child is 13. Its right child becomes 16, and that is red as well. So I'm going to insert 9 and 6 now. When we insert 9, that becomes the right child of 5, and it stays put. When I insert 6, now we're going to have a scenario where we're going to have that kind of zigzag, and it's going to happen is 6 is going to come up, and you're going to see that 6 and 5 end up getting recolored. Then we put in 18 and 20. 18 will become the right child of 16. And then we do some recoloring there. We had the red, black, and red, red parent, red uncle. So we recolored those. And then we recolored the grandparent, which was 14. And then when we insert 20, which is the last insertion of the problem, we see that we're going to have a scenario where 20 becomes the right child, it gets rotated, then 18 moves up. So this is where we get to before we start doing our deletions. So the first deletion is 12. So 12 is the root. So here's what's going to happen. We're going to get the largest value on the right-hand side. The largest value on the left-hand side, and we're going to bring it up. And now what I'm going to do is I'm going to press pause, and I'm going to step through it and describe what's actually going on and how that corresponds to the rules that we discussed last lecture. When we go down here, 9's going to come up, but we're going to see that as of the moment here, in order to get to this node, we go through 2, we go through 2, we go through 2, we go through 2. So when we step forward, we're going to see that it leaves it alone, no rotations. The next step is going to be a slightly more, wait, which one did I delete? Step back. What did I put in? I said delete 12, right? Oh, I'm deleting 9. I put in the wrong value. So 12, I described it already. So 9 is now up here. So if I'm deleting 9, it's now going to try to grab the largest value and bring it up, which is 6. So what happens is it brings it up. Did I say delete 6? I apologize. Okay, so I'm going to delete 9 here. Delete 9. There we go. So now it's going to bring 6 up like so. Okay. So now what we're going to do is we are going to see how the rest of this goes. So we see that we now have an issue with this particular left subtree. What's going to happen is we are now going to color the deleted node, and we see that we have an imbalance over here, and we need to rotate left. So now you're going to see this rotation where 13 will come up because we're now trying to get this rotation. Oh, I'm sorry, I apologize. What we need to do is we're going to see that when this is brought up, we have a red child, we don't have an uncle, and we don't have a grandparent. So in this scenario, what we're going to do is we just need to recolor. Like so. So now we still have the path where all values go to the 2 nodes. So now the last one I have is delete 6. So I'm just deleting roots to show potential issues. So now what's going to happen is it's going to grab a value from the right, and from the left, and it's going to grab 5 and bring it up. So now what's going to happen is it's going to replace the value with a null. You're going to see a null leaf come up here in the animation. And that's in the rule what I said, replace it with a null pointer. That is now going to be that value v, the replacement node. And now we say, well, what happened here is its sibling is red. It doesn't have a grandparent. And now we have this scenario where we see that its a right child is the sibling, and its left child is black. So now we have this situation where we need to perform a rotation. So you see that 14 comes up, and what's going to happen here is now we need to reevaluate the previous value and parent because we don't have an equal number of black nodes to each particular node null pointer. So what we're going to do is we're going to recolor the root, and then the last step we're going to do is we need to recolor 5 and 13. We're going to see that 5 is going to become black and 13 is going to become red. And now we have our final red-black tree. Does anybody have any questions about any of the steps we just went through? Okay, so the big thing with trying to make more advanced data structures to fit your particular application, as we start getting to the advanced topics, is thinking about Murphy's Law. What happens when you have a worst case scenario? The worst case scenario is, let's say we have a red-black tree here, right? And we have a really good red-black tree. We have very good balance. The insertions worked out in our favor. And we just have this one value 2 over to the left that is a little lower than the rest of it, but that's okay. Our red-black tree has done what we needed it to do. Then we take it to our customer. We say, I've got a really good balanced tree. And they say, okay, customer comes around like, oh, that's cool. I need the value in 2. All right, that's the worst case scenario, but that's fine, you have good balance. And the customer says, I need the value in 2. I need the value in 2. I need the value in 2. Like, this is not, I could have just put 2 at the top. This would have made life a lot easier for you and me, right? So the question becomes, how do we account for when the customer wants to do something different than what it is that our data structure came out to be? How can we get the most recently accessed value into the tree? Furthermore, if I was sorting a doubly linked list and I put in all the elements, then I have to go to this worst case scenario. I'd have to sort through everything and put them in at the end. Does anybody remember a term that we learned earlier this semester? And we initially learned it when we were studying dynamic arrays. We were studying dynamic arrays, I said that most of the time the insertion is big O of 1, but we have this worst case scenario where we have to copy them over. But we're okay with this worst case scenario because over time, this one worst case scenario allowed us to be able to do all of the other good ones. And we had some sort of mathematical formula that we learned, and we had a term that we learned with it. Does anybody remember that term? Yes. Absolutely right. The amoritized analysis, the amoritized solution to the problem. So anytime the user acts zany and throws a wrench into our well-laid plans like the Animaniacs, we got to come up with something, our own term. So this is the amoritized analysis that I presented in, I forget exactly which lecture, but the general idea is that we have all of our possible operations. And every possible operation has an amount of time that's required to be able to implement this. So each element, if we add these all up, it should be less than or equal to an amoritized cost of each operation. So we came up with the amoritized cost being the average of all of the operations. And so what this allowed us to be able to do is say, all right, the real world is a little scary, but that's okay. We've accounted for it in our computer science and computer engineering design. So Splay trees, which is the first data structure we're going to learn today, account for this. We are going to try to say, all right, the elements that we've most recently accessed are going to be towards the top of the tree, but we're still going to maintain that same ordering. Now, this Splay tree was invented in 1983, and we're actually going to visit the website of the professor at Carnegie Mellon who invented it, Daniel Slater, because he has a really cool animation I want to show you. It was targeted at cache hierarchies. So in a computing device, if you're in logic design this semester and you've learned about, we have this separation of instruction memory and data memory in order to perform operations. And you might have even learned about load word and store word operations. A load word and store word operation, we've learned about that in the context of call by reference, being able to update the memory in the data heap using a pointer. But then, if you haven't taken computer architecture, the data memory and the data heap is kind of just this magic black box, right? So there's all kinds of ways to do that optimization, which you'll learn about in a lot more detail when you take the computer architecture course. But there's some benefits to learning it now in data structures. This will set you up for success in your careers as well as in future classes. So the whole idea of a cache hierarchy is that, and in fact, I'm going to move over to the left, board left, and I'm going to stop share for a moment. I'll bring this all back up. So help, what's wrong? Right? Everybody can see this over here, help, what's wrong? It's certainly not that you only have 2 more weeks of lecture, right? That's not what's wrong. So here's what's going on inside a computing device. What you have learned, you've learned about this idea. We have registers, and that's where our pointers start. And you've learned about data memory, and that's where we put the heap. And we learned about the stack, and that's where we have all of our instructions, right? So what happens when we exceed the amount of memory that we have in here? These are meant to be fast. I can access what I need to do quickly. So the challenge with fast memory is not that we can't access it, it's that it actually has a real world cost. The faster we can access the memory, the more it's going to cost us. And so in order to get cache, C-A-C-H-E, you got to spend cache, C-A-S-H. So what's going to happen is, in a specific program, I only need a certain amount of memory. Why am I trying to access this large, what we're going to call a non-volatile memory, when I only need to get a little bit of it and keep accessing it? So what we're going to see is you're going to see different levels. So there's going to be a much larger memory block that's a little slower and only costs a little bit. And there's going to be even a bigger one than that. That's slower and it has even less cache. And what we need to do is we're going to grab a certain amount of memory in each portion and bring it back in here. And so the elements that we're going to be using the most often are going to be here. And we want to get it and design our program so that the memory elements happen to be close to each other. So I would want to know where in the memory I need to access. I would want the most recently accessed elements. If I can cluster them together, then we have a well-designed computer program. And this clustering of elements close to each other is known as locality. If I can access this and access it fast with my cache, then I can perform programs faster. And my trade-off, my Amoritized analysis, is the occasional swapping, right? For those of you how many of you are taking computer architecture this semester? What is the term for this? Yes, just for the cache. Yep, we have the loading cache. So you have, when you get the specific memory, you're doing, this is, they might not have covered this specific term. So there's paging, where we bring in a specific page. With cache, we do a cache swap. And so we're going to be swapping certain elements of cache around. Now, what I would like to show you next is I'm going to run a specific command on PuTTY. In this command, I'm going to do ls_cpu. And what this command does is it tells me all the information about the specific computer that I'm running my program on right now. And if I scroll up, you'll see that it's an x86-64. We have CPU op modes 32 and 64-bit. So when we use -M64 in our production quality compilation rules, we're indicating that if there's a choice, we want to use the 64-bit version of the computer. Little endian basically means that I read the bits from right to left instead of left to right. That's something, the benefits of that, you'll cover that in a lot more detail in computer architecture. If we go over the number of CPUs, threads is something you'll learn about a lot more. Threads and sockets, you'll learn a lot more in operating systems. We see that it's an AMD Opteron processor. And I scroll down a little more, it's going to tell me about memory. So L1D cache and L1I cache. L1D stands for L1 data cache, and L1I stands for level 1 instruction cache. So the amount of cache memory in my data heap is 64K, and the amount of memory in my instruction stack is 64K. This is fast, and I'm accessing these as fast as I possibly can. The next level, slightly more memory, slightly slower, costs less, 512K. So I can fit 64 and 64. I make a copy in that's in my level 2 cache, and I say, well, these are the things that I need to run the program. I take them out of that cache and put them into the level 1 cache. So I make a copy, that's faster, I perform those operations, and then I update everything, and that's called cache coherence, and that's something you'll learn a lot about in data structures. Level 3 cache, now we're at 2 megs. So you can see that the amount of memory is increasing each time. So why does this all matter, and how does this matter to us in data structures? So let me read over these two definitions of memory hierarchy, temporal locality, and spatial locality. I will not ask you to identify these on an exam, but it does motivate what we're going to be discussing for the rest of the lecture today. The memory hierarchy is the structure that uses multiple levels of memory in order to improve memory access time. So what that means is the stuff that I'm accessing now, I want that in my fast memory. So this is where the physical memory and the data structure and the code that you're writing all tie together. How do you make this work well? So we use that level 1, level 2, and level 3 cache to improve this. And in order to build on this, we have this idea of the principle of locality, which is basically an example of what I was writing over here. At temporal locality, if a memory element is referenced, it will tend to be referenced again soon. So if I'm using a variable, if you've written programs, use a variable, guess what? Odds are good you're going to be using that variable over and over again, right? And so if you're using the smallest number of variables to complete your task, then we're going to have all those elements close to each other in memory. Object-oriented programming encapsulation take advantage of temporal locality, as well as the next one, spatial locality, by saying, all right, I'm going to put everything close to each other. In an object, we have a pointer. This pointer points to the base address of the class in the data heap, and all the other elements are in that specific order, right? So by applying those production quality compilation rules or having our member initialization lists put the elements in the exact order, we've improved the physical operation, the structure of how we do the data structure, by improving the efficiency of the pointer arithmetic. But what we've also set up there is taking advantage of spatial locality. Having things closer together means it's easier to move them back and forth in this memory hierarchy. And so to follow up on that, the formal definition of spatial locality, if a memory element is referenced, memory elements whose memory addresses are close by tend to be referenced soon. So those are formal definitions you'll see in computer architecture. How that applies to what you've learned now in data structures is you see how using these principles of encapsulation, object-oriented programming, efficient implementation of data structures, if you do that well at the software level of abstractions, and you bear in mind what's going on at the hardware level of abstraction, you will write really efficient programs. Okay, does anybody have any questions on this before I discuss how it is that we are going to implement our understanding of this within a data structure? Okay, let me check the Slack. Okay, so I'm going to, okay, I've described cache memory in detail, shown you all the stuff with this. Okay, so we can use trees to keep track of specific elements in the cache memory. So let's say we revisit this worst case scenario. We were talking about this person who kept trying to access 2. Well, now we see a real world scenario where they might want to do that. They want to take advantage of temporal locality. They want everything sorted. They want to be able to access things fast. And we don't want to use up too much memory. So that rules out hash tables. So now we can use a specific type of tree to provide the balance to be able to find whether or not a specific memory address is within the program, but then get the elements that we are accessing regularly towards the top of the tree. And after a few accesses, what you're going to see is we're going to see that temporal and spatial locality is that benefit in the Splay tree. So Splay tree, the general idea behind a Splay tree is that we are going to have the most recently inserted or most recently accessed elements in the tree are going to be at the top of the tree. So getting the element from near the bottom to the top is this costly amoritized operation. What I'm going to show you in animation is I'm going to have several elements in a tree, and I'm going to say, all right, this is my cache, right? So I'm going to insert 100. I'm going to say values 60 through 68 or 60 through 69 are in a small cache that I want towards the top. And I'm going to show you a set of operations that will get those elements near the top and how that will benefit us over time. And by doing that, we have an occasional worst case scenario, but we're going to get an average case that is good, and in many cases, beats red-black trees. So Does anybody have any questions before I actually go into the machinations of how a splay tree actually works? Okay, so on the left, I have an example of what we're going to call zig. So you've probably heard me use the term zig, zig-zig, zigzag. I've been alluding to the way it's kind of generally referred to in splay trees. But let's say we are trying to splay 3 to the top of the tree. Right? What's going to happen is I need to maintain the order, so I'm going to perform a rotation. 3 is going to move up, 3's right child is going to become 4, 4's left child is going to be whatever 3's left child was. So in this case, 3's left child was null, so that works out. And we now see that 3 is at the top of the tree. So we call this, where it's just to the left of the root, we call that zig. Specifically, we're going to call this zig left. All right, does anybody have any questions about that? All right, the next thing is just going to be zig right. So here, what we're trying to do is we're going to try to move 5 up, and then the rotation is 5's left child becomes 4, 4's right child becomes 5's left child. So in this case, it's null, so it worked out. And then whatever the root is now going to point here. So we now see that 5 most recently accessed is going to be moved up to the top of the tree. The next set of rules are known as zig-zig. So zig-zig means it's in the same direction. Zig-zig left means that the element I want to splay up is left, left, or right, right. So for example, here, this is a zig-zig left. So in this case, I'm trying to move 3 up. So the first thing I want to do is I'm going to perform this operation. We'll remove everything down like we did before, and we see that 3 is now moved up. When 3 gets moved up, 4 and 5 get moved down, like so. And I apologize, for some reason there's a rogue 6 thing that just was there. Pretend that was there before. But now we see that we have our zig-zig. So now what we're going to do is when we move this over, 3 is going to be at the top. 3's right child is going to become 10, and 10's left child is going to become the old right child of 3, which is 4. So we're going to see that. So we're going to have this zig-zig movement, like so. Hey, does that make sense so far? I don't see any questions in the Slack either. So now zigzag is the opposite. So we have a left zigzag, meaning that I want to get 5 up to the top of the tree. What's going to happen is we're going to perform a zig left. We're going to rotate left. So 5 will come up, and then 4 will be the left child of 5. 4's left child will be this null pointer. And then you're going to see that 10's new left child will be 5. And now what I want to do is I want to move 5 up this way. So what we're going to see is that 5's new right child will become 10. 10's new left child will be 5's old left child, which in this case is null. And then 5's old left child is still 4. So we're going to see that this brings 5 up and provides that same searchable binary feature that we had in binary search trees, AVL trees, and red-black trees. So zigzag in the other direction, right, just performs the zigs in that exact way. And we see that we've maintained the order, as I've just alluded to. And so here's another crucial thing. So we're going to go over this access idea, then we're going to work on one problem, and then I'm going to do a specific variant on access, and that will be problem 2. So when we do access, I have a question in the Slack. What are the rules there are for insertions before performing the rotations? I'm going to describe this in a little detail, but the general rule, let's say if I'm inserting 1, I would put 1 here, then I would keep splaying it all the way up to the top. So you would insert it as you would in a normal binary search tree. Please let me know if that addressed your question. So with access, we're going to perform this rotation. So I'm going to say I'm going to access 3, and then I'm going to start moving it up. So we're going to see that 4 is going to become 3's right child, like so. And then what's going to happen is 10 is going to become 3's right child, and 10's left child is going to become 4. And so now the most recently accessed element is at the top of the tree. The next thing we're going to do is we're going to access 4. So what we're going to see is we have a zigzag to the right. So we're going to rotate 4 such that 10 becomes the right child of 4, and 10's left child becomes 5, like so. And then what's going to happen is we're going to rotate this way. 4's left child is going to become 3, 3's left child is going to become the old left child of 4, and 3's right child become the old left child of 4, which is null in this case, and moves it up. We still have the same search capability, and the other thing I want to point out is note how 3 and 4 are now closer to the top of the tree. Yes, you have a question? Sure. So here's what happens. So in this case, what happens is we are accessing 4. Our goal, we have 2 goals. One is get 4 to the top of the tree. The other is to maintain ordering. So what's going to happen is 4 is going to rotate up here. So 4 will become initially the right child of 3, right? 3's old right child was 10. So we know that 10 is greater than 4. So we're going to perform this rotation. 4's old right child is going to point to 10. But we still have to maintain the ordering. So what's going to happen is 10's left child is going to point to 5. So we'll come down here. And so we see that that's what's happening here. So if I want to see is 5 in the tree, I would go to 3, 4, greater, 10 is greater than 5, so I go left and I find that. So it maintains the ordering. Did that address your question? Awesome. And Nick, I'm happy to see that addressed your question as well. Does anybody have any other questions before I continue? Okay, so we see that 3 and 4 are closer to the top of the tree. And so what I'd like you to do now from the folder that you just did, let me run clear, make prob1. And what we're going to do is we're going to do a set of insertions. And all we're going to do is insertions for the moment. And so the insertions are 1, 10, 2, 9, 3, 8, 4, 7, 5, and 6. I hope I have that right. It does have the final exam study. Well, I'm not even close to correct. I know the answer will come out. So instead, what I want you to do, my apologies for this, please do 10, 7, 15, 22, 8, 5, and 9. The link that's here is going to take you straight to the lecture 24 portion of the final exam review guide. So it'll open up like this, and it's taking its split time. There we go. So it should bring you here. So problem 1, please follow those directions. I'll give you a few minutes to do that, and I'll walk you through the steps on solving this problem. All right, someone take me through the process of the first two insertions, so 10 and then 7. Yes. Hmm? Absolutely right. So what's going to happen is we start out, 10 gets inserted, and then it goes to be the left child. And then we perform a zig, so then 7 becomes the right, 7 becomes the root, and 10 becomes the right child. So now what's our next step? So we're inserting 15. What's going to happen? I'll also bring out my phone so that way those of you on the, oh, I'll turn my phone on. Who wants to help me out here? What's going to happen with this? Yes. Yep, it's going to be a zig-zig. So what's going to happen is we're going to see that 15 gets moved up, and then we're going to see that 15 comes here, 7, and then 10. So that's how the ordering works as well. So from there, we're going to have, let me go a little quicker. We got 22, so 15 would be, 22 would end up here. It's going to zig up, and therefore 22 becomes the root, 15 becomes the left, 7, and 10. From here, now 8 gets inserted. So 8 would actually end up down here initially. So when we do a zigzag, what we're going to see is that this will initially become, just this subtree will become 8, 7, and 10, and then 15 will become the new parent of 8. Does that make sense so far? From there, we're going to see that we have a zig-zig. So from what's going to happen is 15 will become the right child of 8, and then 10 will become the left child of 15. So this becomes now 8, 15, and 10. 7 still over here, 22's up here. Then the last step becomes, well, we're going to move 22 up here. So now 8 becomes the root, 22 is to the right. The new left child is 15. And so everything remains the same down there. 7's over here, and that means 10 is the left child over here. Does that make sense so far? Let me bring up, oh, just never turned. I apologize to everybody in the Slack. My phone is still off. Okay, so now we're going to insert 5. 5 would be over here. So now we have a splay, so it's going to become 5, 7, and then 8. Like so. And then finally, we're going to insert 9. We insert 9. 9 initially comes all the way down here. And then we see we have a zig-zig. So that's initially going to become 9, 10, and then, so 9, 10, and 15 was like so. And then if we move this up here, 9 is going to become, 15 is going to become the right child of 9. And 10 gets moved down here. And then 8 is now currently the right, so 9 is currently the right child of 8. So we have this scenario where we have a bunch of zig-zigs. So 8's going to come down. And eventually, we got 7 up here. Then what's going to happen is we're going to move this down. And when this comes up, left child of 9 is going to become 7. 7's right child is going to become 8, like so. And then the last thing is 5 is going to be there. So then we just do one more zig, so it becomes 9. 9's left child becomes 5. And all at the same time, we have everything moving up here. So 9's right child was always 15. It's going to remain that way down below. And then from there, we have 7 and 8. I believe the choice is A for the correct answer. Does everybody see how that zig-zig and zigzag works? Let me move back up to the main podium and share the screen. All right, so once you do that, it should be prob1.text should now be visible. So let me go back and show you one aspect of Splay Trees that's really important. So because we're trying to access cache memory, or that was the main initial goal, one thing that became clear to the inventors is that if the element isn't in the Splay tree, we want to splay the closest value to that into the top of the tree. So for example, in this particular data structure, I want to find 6. So I'm going to have an access of 6, but we see that 6 is not in the Splay tree. So here's what's going to happen. We're going to go down. 6 is greater than 4, 6 is less than 10, and then we get to this point where we can't go any further. So the closest that we can get to 6 becomes 5. So what's going to happen is 5 is going to splay up. Here we have a zigzag. And then that is our solution. Does anybody have any questions about that? So we're going to do the same thing. We have find 18. Well, 18 is not in the tree. So what we're going to do is we're going to say, well, 18 is greater than 15. We get to 25. We're at the end there. This means we're going to splay 25 to the top. Like so. All right, does anybody have any questions about this before I discuss the benefits of the Splay tree and why it's constructed this way and then go into problem 2? Yes. So what's going to happen, you're asking about, and I apologize, it's raining, so I'm having a bit of a hard time hearing everybody. But what's going on is that if the element is not in the Splay tree, so for example, in that last one, I said find 18, 18's not there. The value that's closest to that element in the Splay tree is going to be splayed to the top. So in this case, it's always going to be a leaf, and then we will get through and complete, it moves up there. And I'm going to discuss why it is that we have a benefit of this here. So this is we'll address your question in more detail. So revisiting building credit and Amoritized analysis. So binary search trees and Splay trees have this worst case scenario where we could potentially just have it be a glorified linked list, right? So let me bring up an animation page and show you. So I'm going to do Splay Tree. And if I start inserting values, let's say insert 1. If I insert 2, 2 gets splayed to the top. If I insert 3, 3 gets splayed to the top. If I insert 4, 4 gets splayed to the top, and so on. So the more that I insert, we have an initial worst case scenario. But it turns out this is okay. This is our Amoritized trade-off. And the reason why this is okay is because that's how a memory is initially set up. We initially set it up in just a long line. So the Splay tree, if we insert all the addresses in the order, is initially looking just like the physical block that we are putting elements into the data heap. The question becomes, how do we know which elements represent this, this temporal and spatial locality? So for a binary search tree, I've calculated the amortized cost of that worst case tree scenario that we had. And if these are visited in order, here's what's going to happen. So with these accesses, let me bring this back up. I'm going to insert 5, 6, and 7 and show you the benefit here. We're going to get 6, and actually I'm just going to do that enough because I don't want it to go outside of the animation. But let's say I want to access 3. So I'm going to say 3 and find. So now it finds it, and it's going to perform the splay. And then if I want to find 3 again, so there is our temporal locality. Now it's at the top. And now I can say, well, if I want to find 2, now that element is close. I know that, let's say 2, 3, and 4 are really close to each other. So now what's going to happen is 4 is going to get splayed above 6, and we're going to see that 2, 3, and 4 are closer to the top. So if I do 3 again, this will splay everything up. So now the elements that I've most recently accessed are 2, 3, and 4. The benefit is that I'm going to get this percolation of elements to the top. So there's all the stuff that I just showed you. And the crucial thing is we are able to beat 4 by performing these splays. So now our amoritized cost compared to a binary search tree is coming down. The other thing I would like to show you is this link. So this particular animation was developed by Daniel Slater, who's a professor at Carnegie Mellon and invented Splay Trees. And what this animation does is it's going to, I'm going to say I want 100 nodes. And here's that worst case scenario I was telling you about. See, I can go all the way down here, and it goes through 0 through 99. Does everybody see that? So what's the benefit here? Let's say that I want to use this to represent cache, and the cache memory that I want to have it around is in the values from 60 to 69. So what happens when I first, let's say I click 63. That's the first memory element that I access. So this animation, I can click 63, and what's going to come up next is that 63 is going to be splayed to the top of the splay tree. We now see that these values are up here, but we have 60, 61, and 62 down here. So now let's say 63, I want to access 66. It'll re-on it. We see that the values 63 through 69 are still closer to the top. But now let me click on 61. When I click on 61, we now see that 61 through 69 are close to the top. Now I want to click on 60. And now 60 is at the top. And now I'm going to go back and forth. In a typical cache, you might have hundreds or thousands of accesses before you would want to splay again. So let me pick 66. And we now see that all these elements are here at the top. If I pick 64, it gets splayed, and it's much quicker. I can do 69 here. I can do 68. I can do 67. And you see how all those accesses now become really quick because they're now closer to the top of the tree. If we have a non-uniform access, splay trees become significantly more beneficial than a red-black tree. It's just like when we chose prime numbers as the size of our bucket in a hash table, because we want to account for a situation where non-uniform access is beneficial. Does that make sense to everybody? Okay, let me check the Slack. I don't see any questions. And so here in the slides, I have an example. And so what I did is I took the math from a splay tree here. And if we have a non-uniform seeking for this particular set of operations, I calculated between 50 and 60. And how many, and this is the balance of the relaxed balance red-black tree. We would see that splay trees, for the number of accesses, improves upon red-black trees for non-uniform access. So if it's uniform, meaning that we're going to be accessing the elements equally, or, and this will tie into the rest of the lecture, the probability that the elements that we access are equal, then a red-black tree is good. If we have a scenario in which we anticipate clustering, for example, locality and physical memory, then a splay tree becomes beneficial. Does anybody have any questions before I move on? All right, so in the interest of time, what I would like to do is I have a problem here for problem 2, and what we're going to do is we're going to work through this together. So the specific problem that we're going to work on, we're going to insert 10, 7, 15, 8, 12, and 6. And 12, 16, and 11. And then we're going to do finds on 8, 13, and 11. And so one thing I want to point out is that when I present this question on the exam, I will have an element in the list of finds that I did not initially insert. If I were to do this in a binary search tree or a red-black tree or an AVL tree or a B tree, and I say, find me that element, it's going to say it's not there, and it will leave the structure alone. In a splay tree, our objective is to find the element that's the closest and splay it up. And so let me bring that animation back up, the other one. And this is a good one to, if you're developing your own problems to try to practice for the exam, these web pages are really good to help you practice elements of these data structures. So first, let's insert 10, 7, and 15. So 10 becomes the root. 7 is going to become the left child of 10. And then it will splay up. Now I'm going to insert 15. And 15 is going to become the right child of 10. And then let me pause, and then we'll step forward. And we see that we have that zig-zig, and now it moves everything up. So now we're going to insert 8. If I insert 8, 8 is going to become the right child of 7. And then we're going to have that zigzag. And then we have a zig. And that is our new scenario. Then we're going to insert 12. 12 is going to become the right child of 10. And then we have a zigzag. So 12 is now going to move up. And then we have a zig. So 12's left child is going to become 8, like so. Now I'm going to insert 16, which will become the right child of 15. And we see when we get here that we now have a zig-zig scenario. So now 16 is going to become the root. Its left child will be 15, and the 15's left child will become 12. Finally, we have 11. 11 will be down here, and then we're going to start splaying it up to the top. So we see that we initially have this zig-zig. So 11's left child is going to become 10, and 10's left child is going to become 8. From now, we have a left-left zig-zig. And now 10's right child is going to become 12, and 12's right child is going to become 15. And now we have a final zig. We're going to have an 11. 11's right child is going to become 16, and 16's left child is going to become 12. Does that make sense before I move on to the accesses? For the accesses, we are first going to do 8. And we see that 8 is down here, almost at the bottom. So let's watch what happens. It's going to first find it. There it is. We have found 8. And so now we see zig-zig. Does that make sense? So now 8's right child is going to become 10. 10's right child is going to become 11. Does that make sense so far? All right, the next thing we're going to do is 13. So this is something that you're going to see on your exam. 13 is not in the splay tree. So what's going to happen is we're going to say, well, 13 is bigger than 8, 13 is bigger than 10, 13 is bigger than 11, 13 is less than 16, 13 is greater than 12, and it's going to get down here to 15. And 15 has the null children. So what it's going to say is if 13 is not in the splay tree, it's going to go all the way down until it can't progress any further, and it's going to say, well, 13's not in the Splay tree, but 15 is. So 15 is the element I need to splay up. So now we have a zigzag scenario. So we're going to see that 16 is going to, it's going to be 15, my apologies. 15 is going to move up. 15's left child is going to become 12. And 15's right child is going to become 16. We now see that we have here a zig-zig. So 15's new left child is going to become 11. 11's new left child is going to become 10. And 11's right child is going to become 12, which was previously 15's left child. Finally, we have one last zig to do, and that's going to be 15 is going to move up to the root. 15's left child is going to become 8, and 8's right child is going to become 11. And so that's how you do it in a scenario in which we do not, the user requests that we have this, and they are unable to get there. We're unable to find it. We splay the closest element to the top. And the last one is 11. So we see that 11 is a little down here. So we're going to come up here, and then we see that we have a zigzag. 11's new left child is going to become 8. 8's new right child is going to be 10. And then we move up, we're going to see that 11's new right child is 15. 15's new left child was 11's old right child, which is 12. And if I remember correctly, this is choice A here. Okay, does anybody have any questions about that? And that should be make prob 2, and that should be A, and that is the correct answer. All right, so the next thing I want to do for the last 15 minutes of lecture today is introduce another data structure and talk about the benefits of it. And we'll go through an example problem. Now, when we have in the Splay Tree scenario, what I talked about is when we have a non-uniform access. So we saw that there's a physical application where non-uniform access benefits us. Now we have a potential of probabilities. And this is where you start going into, for those of you who haven't taken discrete math, you can start applying probabilities to doing advanced algorithms. For those of you who have taken discrete mathematics, this is a preview of things that you will see in the algorithms course, where how do we account for scenarios where I know that there's a certain probability that I will access it, and I want those probabilities to be reflected in the balance of the tree. So if there's an 85% probability that I'm going to access a specific element, ideally I want that higher in the tree than if there's a 13% access. Does that make sense? So we're going to take advantage of that knowledge to take advantage of probabilities in searching for our trees here. So we're going to balance, we're going to have a binary search tree that but also takes advantage of priorities. So here's what we're going to do. This data structure is going to be a combination of a tree and a heap. We combine that together and we call it a tree. The idea of a tree is that it has a binary structure where we are able to find an element in sorted order. So for example, if I want to find the letter H here, I know that I can search for it this way. So it maintains the in-order property of keys. However, we are going to heapify such that the elements that are closer to the top have a higher value. I'm sorry, have a higher probability. So we're going to have some sort of numeric value, and the values that are closer to the top will have the higher probabilities, but it'll have that sorting. So we're going to do the heapification with the probability, but we're still going to have the sorting capability in the tree. So we get around one of the big issues in heaps, which is that it's really good if we want to find the smallest or largest element, but it doesn't have a sorted underlying structure. But the benefit of the tree is the searching. But the heapification benefit allows us to be able to take advantage of high probabilities. So what I have, so this one was invented in 1989, and the big thing that we're trying to do is evolve averaging out to a good worst case scenario. And so I'm going to go over a problem with you, and then I'm going to present some math to show you the benefits of this data structure compared to a red-black tree. Another big thing that we're going to see when I run the code example is that if we're using, say, rand, if we're using random, this means that the data structure that we will produce will be unique every single time. Does anybody remember from lab 7, when we did rand, what it's actually returning? Does anybody remember what the data that's coming from when we ran that specific function, that C++ function? Does anybody remember that? See if anybody mentions it in the Slack. So when I called rand, and I actually alluded to this as there's a specific problem with the thing that it was returning to. Is this starting to ring bells? The random number generator returns what? Is the rain on top of the step-in center putting everybody to sleep? I saw some nodding of heads, like, yes, this is really, it's starting to make me feel like I just want to cuddle right up here and take a nap. The rand returned the number of seconds since January 1st, 1970, right? And it returned it as an unsigned integer. And you went into this whole thing about the challenges with that and why that in 2038, that's going to cause all kinds of issues. And that was, in that context, we were discovering why it is that it's important to understand the difference between a float and a double, a long unsigned and an unsigned int. Because of that, every single time I would run this, I will get a unique treat. It's just based on the numbers that are generated. And so for now, I'm going to skip over the code aspects of it. Let me show you how this insertion works. So the difference between a normal binary search tree node and the tree node, it has a left and a right, but it also contains a data as well as the value corresponding to the probability. So first I insert D and the number 60. So what's going to happen is, let's say I now insert F with a priority of 75. The steps that we're going to follow are that we initially insert to the right, because F would be the right child of D. But then we have a heapification. We now want to maintain the ordering. And so we're now going to see that F's left child is going to become D. And the reason why we do that is because 75 is higher than 60. I have a higher probability of accessing F than D. Therefore, I want F to be higher. Now, if I do H in 14, 14 is less than 75, so it stays put. Now I want to do C in 70. So here's what's going to happen. 70 is going to push 60 down. The right child of C70 is going to become D60, like so. 70 is less than 75, so C stays put in the tree. A55 stays there. So we know that all of the children of 70, everything below 70 has a lower probability. And it's sorted, so we can actually figure out whether an element is here. So now if I was 65, what we're going to see is I is going to come up, and H is going to become the left child of I. And if I put in G and 80, we're now going to see that H, that's 60, initially its right child is going to become H and 14. But then we're going to see that G's right child is now going to become I and 65. I's left child is going to become H14. And now we're going to move this up. G's left child is going to become F because 80 is higher than 75. Does everybody see that? Okay, so, all right. So this particular slide, I'm going to show you make tree insert. And when we run this, we're going to see the in order, pre-order, level order, and post order for those exact insertions that I just showed you. The thing that I incorporate into the next step is using random. So in this in treep3.h, when I insert a value, I'm using that random number generator from 0. I'm going to mod it by 100, and that's going to be its randomly generated value that we're going to use to insert. So we're going to sort, we're going to use insert with root value and a priority. And then when we do the insertion, then we splay it up to the top. And so what it's going to have with make insert random is that when I run this, each time we're going to get different results. So the first time I run it, if I make insert random, it's going to give me a specific ordering of the tree. But if I do it again, it's going to give me a different tree because it's basing it off of the random number generator. Right, so I run it again, I get a different tree. And so let me skip over this. So comparing max height to the other trees. So I ran an experiment where I generated 10,000 random generated trees and then compared it to the final result for a red-black tree with the exact same insertions. And so what's going to happen is for 100 random inserts, for a red-black, it's actually going to come out to, over time, 3/2 log of n plus 1. And we know that a red-black tree is 2 times log of n plus 1, which means over time, what we're going to see is that the tree is going to beat the red-black tree. So if I run 100 random inserts on a tree, and then I run the experiment 10,000 times, what we're going to see is that based on that math I showed you, the most common was 10, and then 9, 11, and 12. And see that occasionally we get out here 14, 15, and 16 in the worst case height of the tree. Over time, we see that 95% of the trees had a better max height than the worst case red-black tree, and 95.85 had better or equal max height. So the benefit becomes, what do we actually want? Do we want it to be consistent every time? Do we only need it to be relaxed? If we know it needs to be consistent and relaxed, that's when we use a red-black tree. So that's why you see standard set, standard map, standard multi-set, all used red-black trees because that's beneficial. We know what it's going to be every single time. If we have non-uniform access, we want to do splay. Splay will beat red-black trees in non-uniform instances using Amoritized analysis. And if we want to have correlation, really good balance with respect to probabilities, we have a set of known probabilities, then a tree data structure will be beneficial for us. So deletion from a tree, we're going to do standard binary search tree deletion, and then we're going to do a heapify type process. So what I'm going to do is I'm going to take the last 3 minutes of lecture, I'm going to go through it, and then on Tuesday we're going to complete the problem together, and then we're going to spend the rest of Tuesday's lecture going over a new type of data structure that you'll see a lot in the algorithms course called a binomial heap. So let's say we want to delete F. When we delete F, we're going to move the largest element on the left up. So initially, we're going to move D there. So when I say largest, I mean the key, not the largest by probability. So that's our binary search tree understanding. From there, I'm now going to perform heapification. I see that the value C to the left is bigger, so I'm going to move C up and move D down. Does that make sense? From there, what I'm going to do is I'm going to say, well, I want to delete C. Now I move A up. I see that D is too big, is bigger than A. So we're going to rotate left, and now D is there. Now I want to delete 80. The largest element on the left is D. So D is going to move up. Oh, my animation's off. I'll draw it out. So what would happen is D would move up to 60 here. I have A55 on the left and I65 on the right. So what will happen is this is going to move up. It'll become I65, and then its new left child, D60, would be here. All right, does anybody have any questions about this, about treats or splay trees? I'll go over the problem to start Tuesday's lecture. So I'll give you an idea of the type of problem that you'll see on an exam. Then we'll go over binomial heaps. And binomial heaps are basically an improvement upon max and min heaps. All right, if no one has any other questions, it's now 2 o'clock, and you all have a wonderful weekend. The memorandum 2 directions are up. Please make sure you complete your second code review. I am getting flooded with compliments from your mentors, so I know that you all are doing extremely well and that your proposals were outstanding. And on that note, we are less than 2 weeks left. So keep up the good work. I know this has been a challenging year. And on that note, if you don't have a lecture, get a little nap. If you do, I didn't tell you to nap in another professor's class. I did not tell you that. So you all have a wonderful day, and I'll see you next week.